Today we will discuss about relative lowering of vapor pressure. Relative lowering of vapor pressure means there will be lowering in the vapor pressure, means there will be decreasing in the vapor pressure. We will discuss at what conditions there will be decrease in the vapor pressure. Let us consider water. Now water is taken in a beaker. Let us consider that this is closed. This is closed now. It is filled with water. If it is filled with water, you know that there will be the water from the surface which is changing into vapors. These water molecules, some amount of these water molecules will change into vapors. That will be giving some pressure, and that is known as vapor pressure. So this is the one which is the vapor pressure of, if it is water, then this is vapor pressure of water, right? And this evaporation process, it is a surface phenomena. You know, the boiling point of water is 100 degrees Celsius. But when you keep water in the outside, right, you will be noticing there will be decrease in the water level. Why that is happening? Because the water in the surface will change into vapors, right? It will be taking energy from the sunlight or from the surrounding, and it will change into vapors. So these vapors are giving some pressure here, that is known as vapor pressure. As this is the water, as it is water, it is known as vapor pressure of water. This is the pressure. Now what I'm going to do is I'm going to add some non-volatile solute. Non-volatile means which is not changing into vapors. I'll be adding, let us consider I'm adding some salt. Some salt is added. Now if this is added with salt, you are mixing it well. It will be giving a mixture, right, which is known as homogeneous mixture. That is also known as solution. The solution is formed. This is the solution. Now, where is that salt which we added? We added some salt. Where is it present? To find out now, if this is a beaker, if this is common salt, when you touch this part, when you touch this part and when you taste it, you will be noticing it is salty, right? When you touch this part, when you touch this part, and if you taste it, you will be noticing it is salty. It means what? That the salt particles are dissolved completely. It is uniformly spread. So everywhere the salt is present. Now let us compare this solvent and solution. In this solvent, the water molecules can evaporate. These water molecules will change into vapors from all the part. If the area of this part, is, for example, if this is 1 centimeter square, from all the 1 centimeter square, there is a possibility for the water to change into vapors, right? But when you consider the second one, the solution part, when you consider in that solution, if this is 1 centimeter square area, right? But out of this 1 centimeter square, definitely there will be some part, right? The surface of some part which is not having water, instead it is having that salt. So here, though it is 1 centimeter square area, but water molecules are not present in that 1 centimeter square area. But in this solvent, if it is 1 centimeter square area, from that 1 centimeter square area, from all the part, there is a possibility for the vapors to, for the molecules to change into vapors. So this will be giving more vapors. This will be giving more vapors, and this one will be giving less vapors. If more vapors are there, this will be creating more pressure. So here more vapor pressure, and here it is low vapor pressure. This is known as lowering of vapor pressure when there is a solvent, when some solute particle is added which is non-volatile, then that will be occupying some space on the surface of that solvent. That will be stopping some amount of water molecules, or that will be occupying some surface, so that from that one the liquid or the solvent is not changing into vapors. So because of that, in first case there will be more amount of vapors. In the second case, there will be less amount of vapors. So this is known as lowering of vapor pressure. Vapor pressure is decreased. Here more vapors, here less vapors. That is known as lowering of vapor pressure. If you consider the vapor pressure of this solvent, if you take this as P1 naught, if this is P1 naught, and in solution you are taking it is P1. What is this? Vapor pressure of solution. What is P1 naught? Vapor pressure of solvent. What happened in this case? The vapor pressure is decreased. Here it is more, here it is less. So how much it is decreased? It is decreased. How much it is changed? That one is lowering of vapor pressure. Lowering of vapor pressure is, that is equals to, it was P1 naught and it has become P1. This is the change in the vapor pressure. As the change is decreasing, you will say lowering of vapor pressure. What is relative lowering of vapor pressure? Relative lowering of vapor pressure. Relative lowering of vapor pressure is, see, the lowering of vapor pressure is P1 naught minus P1. How much is the change compared to the initial one? What is the initial one? The initial one is P1 naught. So this is how it is related. How much it is changed? This is P1 naught minus P1. When you are comparing with the initial one is P1 naught. This is known as relative lowering of vapor pressure. This relative lowering of vapor pressure, you can write this as it is a change, right? You will take it as delta P by P1 naught. This delta P divided by P1 naught. That will be equal to, you just think how much the change will be, that depends on how much amount of the space is occupied. The previous case, here how much the space is occupied, right? If the space occupied by the solute is more, then there will be low vapor pressure. If it is less, then there will be more vapor pressure in the solution. So it completely depends on how much amount of the solute particle we are taking. So you will be writing mole fraction of solute. The change, that will be equals to mole fraction of the solute. It does not depend whether it is sucrose or glucose or any other. It completely depends on how many particles are there. It depends on number of particles, how much space it is occupying, right? So number of particles only it is depending on, and that is why this is also known as colligative property. P1 naught is equal to vapor pressure of solvent. Delta P equals to change in the vapor pressure. So you will be taking initial one is solvent, the final one is after adding the solute. So change in the vapor pressure. And P1 equals to vapor pressure of solution. Chi1 equals to mole fraction of, take it as you are taking for solvent 1, right? So you take it as 2. So Chi2 equals to mole fraction of solute. Right? So delta P or P1 naught minus P1 divided by P1 naught equals to mole fraction of solute, which is also equal to number of moles of solute divided by number of moles of solvent plus number of moles of solute. N2 divided by N1 plus N2, where N2 equals to number of moles of solute. N1 equals to number of moles of solvent. So this is the formula. If it is more diluted, if the dilution is more, it means that if dilution is more, it means that there will be more amount of in more diluted solution or in diluted solutions. See, diluted means there will be more amount of solvent and less amount of solute. So the number of moles of solvent, number of moles of solute. As number of moles of solvent is more than number of moles of solute, you can write this as P1 naught minus P1 divided by P1 naught equals to N2 divided by N1. Why we are neglecting N2 in the denominator? Because N2 value is very small. It is like you are adding two numbers. Let us consider why this is to be done, right? Why you are writing N2 by N1 plus N2 by N1 instead of N2 by N1 plus N2. It is because if you take this value, and you are adding this one to this one, then how much is this? 1 lakh is added to 1, you are getting 1 lakh and 1. This is the thing. Here, if you take number of moles of the solvent is N1, number of moles of solute is N2. By adding number of moles of solute to the number of moles of solvent, it is not going to make a big change. That is why in the denominator, when it is in addition, if one of the substance is very low, the other substance is very high, the number is very high, then the one which is very low can be neglected. When you are adding that and when you are making a calculation, that value when you are comparing with not adding and doing the calculation, both will be nearly the same. That will not make a big change, and that is why it is neglected. Understood? And finally, this RLVP is one of the colligative properties because it depends on number of particles. It does not depend on which particle, what is its nature. It completely depends how many particles are occupying that space. That's it. Thanks.